Chapter 19 in the Abstract Algebra series is going to be an overview of many of the topics discussed throughout the series, sort of combined into one lecture. So let's look at S3. Remember that S3 is a set of elements that each represent a unique permutation on the set containing the integers 1, 2, and 3. And since we have three elements, 3 factorial being 6, that gives us the number of permutations on the numbers 1, 2, and 3. And I decided to designate each of the permutations as P0, P1, up to P5. In other words, S3 is the set containing the 6 different permutations. And notice from the Cayley table that if you multiply any 2 permutations together, you get another permutation. So this binary operation has closure. Notice that the identity P0 is listed in each row and in each column. And notice that each element has its own inverse. For example, if you were to look at, let's say, P4, notice that P4 times P5 gives you P0, which is the identity element. And if you were to go by item and check each element, you would see that they do each have a unique inverse. And of course, when we multiply permutations together, we do so in the same manner that we do the composite functions, which means we start from the right and work our way to the left, as we've talked about a few times throughout the series. And multiplication of composite functions is, of course, associative. So since we have closure, we have binary operation, we have the closure, we have the inverses, the identity, and associativity, we know that S3 does comprise a group. And just to recap here, I'm just going to read what I have written down. Notice that each row has no duplicates. Also, each column has no duplicate elements. Each row and column contains the identity permutation P0. Each element does have an inverse. The inverses of P0, P1, P2, P3, P4, and P5 are P0, P1, P2, P3, P5, and P4 respectively. The table again does verify closure. So since we have all 4 requirements for a group, S3 is indeed a group. Remember that according to Lagrange's theorem, that the order of any subgroup H of G must divide the order of G. So let's examine H, where H contains the elements P0, P2, and P4. If H contains P0, P2, and P4, we know it's a subset of S3, but this would not be a group because if you multiply P2 times P4, you get P3, which is not an element in H. And I highlighted this example just to verify that just because the order of a subgroup, or a subset rather, divides the order of the group, that does not guarantee that you have a subgroup. Sometimes you simply have a subset. But let's look at a subgroup. If I let H be the set containing the elements P0 and P2, we do have a subgroup here. If you look at the Cayley table, notice that we have a closure and we have all of the other properties that we talked about. Remember, when dealing with subgroups, we can just check the CI property to verify that we have a subgroup. We do have closure because if we multiply any 2 elements in this H together, we get another element in H. And notice that every element does have an identity. In fact, has an inverse. The inverse of P0 is P0, and the inverse of P2 is P2. So since we have closure and we have inverses satisfied, we know that we do have a subgroup in this case. And once we have a subgroup, we can then partition the group by H. So how do we do a partition using H? What I tend to do is I tend to write down H and its corresponding elements. And then since the cosets cannot overlap, I choose an element that is not in H. And I chose P1, and then P1H gives us the left coset that contains P1 and P4. And then I chose another element that has not been used, and that would be P3. And P3H gives us P3 and P5. This exhausts S3. There are no other elements to choose, which means that the index of S3 by H is 3, because I have 3 cosets using this subgroup. Notice that the order of S3 again is 6. The order of this subgroup is 2. And the index of S3 by H is 3, which is a fancy way of just talking about the number of cosets. And again, there's a theorem out there that verifies that if you take the order of a group, it is going to be equal to the order of the subgroup times the number of cosets that are generated. This just kind of is an example of that proof, because 6 is equal to 2 times 3. Any other subgroup of S3 will also partition S3 in a similar manner. And note that this partition does give left cosets of H. And since S3 is non-abelian, the right cosets could be different. You would need to check that. Let's take a look at Z4, where Z4 is the set containing the integers 0, 1, 2, and 3. And if we look at H, where H contains the elements 0 and 2, this is a subgroup. And we can verify that, because if we add 0 plus 0, we get 0, 2 plus 2 is 0, and 0 plus 2 is 2. We have closure, we have inverses. Each element is its own inverse. And again, by the CI property, we know that we have a subgroup here. And that means we can partition Z4 using this particular subgroup. And just as we did in the previous example, we start with H. Then we choose an element that is not in H. And of course, since we're using integers here, we are going to let addition be the operation. And 1 plus H gives us the left coset containing the elements 1 and 3. Notice that these two cosets exhaust Z4. And if I draw the picture, it would look like this on the right side. Notice that I have taken Z4 and I have split it into 2 cosets, one being the subgroup H and the other being the subset 1 plus H. This is the entirety of Z4 partitioned according to H. Notice that the intersection of the 2 partitions is the empty set, which means they cannot overlap. And if you look at the union of the 2 cosets, you get Z4. And this completes the definition of an appropriate partition. Okay, let's review isomorphism. Remember that 2 groups are isomorphic if they have the same structure. And for simplicity, I chose to look at Z2, which contains the integers 0 and 1, and then group G, which contains E and A, where E is the identity. These are going to be isomorphic to one another because I can actually map the 0 to E, and I can map the 1 to A. In other words, I can just let 0 equal E, 1 equal A, and I can substitute into either table, and I would generate an identical table. One thing we need to do to ensure that we have an isomorphism is to make sure that we have an operation preserving situation, and we do that by verifying that phi of G1, G2 is equal to phi of G1 times phi of G2. Notice that in this case, we have 0, and 0 is 1 plus 1. Well, with the image of 1 plus 1, would that image map to phi of 1 times phi of 1. And we have to use times on this side because that is the operation for group G. And of course, we added on the left side because addition is the operation in Z2. But I have to show that this 0 here, again, which is just phi of 1 plus 1, does it map to phi of 1 times phi of 1, which is the identity. And if we go through each case, we can see that that is structurally sound. We do have the operation preservation here. For example, if I take, again, phi of 1 plus 1, which we know is 0, the image of that is phi of 1 times phi of 1, which is a times a. And again, that gives us e. So that checks. And if you look at phi of 0 plus 0, 0 plus 0 is 0. And notice that phi of 0 times phi of 0 is equivalent to e times e. And we see that both of those are true. And then finally, if we look at 0 plus 1, phi of 0 plus 1 is the same as phi of 1. And we know that phi of 1 by our mapping is a. And we show that that's equivalent to phi of 0 times phi of 1 in G, because that gives us e times a, which is equal to a. In other words, we have verified that this statement here is true. Typically with larger groups, you have to look at the structure of the groups, and you have to let your G1 and G2 values be arbitrary. But since these two groups are small, we could actually do them pairwise to verify that indeed we do have operation preservation here. So this lesson basically serves as a review of binary operations on sets, groups, and subgroups. We talked about the order of groups and subgroups. We looked at Cayley tables. We discussed Lagrange's theorem. We did not do any proofs on Lagrange's theorem. We did do some applications. We talked about isomorphisms. We talked about left cosets and partitioning groups. I hope this overview is helpful, and I appreciate your listening.